let's get started. All right, so today is the last the lecture of the session 1 or part 1 of this course, and today we are going to deal with the liquid phase simulation and also some of the advanced topics. I will demonstrate some, the practical applications that you may encounter in the research. Okay, so in the liquid phase simulations, we are going to talk about the 3 topics. The first one is the, sorry for the interruption. And so the first topic is about the radial distribution functions which characterize the liquid phase in terms of structure. And since in the liquid, the atoms are move around freely. Okay, so the relevant constant is the diffusion coefficient or the self-diffusion of the atoms that comprising the liquid phase. And the last, so once you can simulate the liquid phase, one thing that you can utilize or exploit is the melt and quench simulations to obtain amorphous structures that are widely used in the recent industrial applications. All right, so how to simulate the liquid. So in the last lecture, we have learned about how to control the temperature. Okay, so maybe you can simply thinking that if you raise your temperature above the melting point, maybe the system will melt and so you can such that you can simulate the liquid phase. But however, the important thing is the starting point. Okay, so if you start for initial structure as a crystalline phase, and if you raise temperature above the melting point, it does not still the melt for the time being, because the phase transition between the solid and the liquid requires incubation or nucleation of the liquid phase. So in the material, you have totally solid phase, so every atoms are ordered, and in some part of the solid, you may have some of the randomly the moving atoms or the nucleate a small part of the liquid phase, and it will grow. All right. So this is the usual typical picture of the homogeneous nucleation mechanism or the phase transition. All right. So, but this nucleation and growth, it requires time, and in reality, maybe at least around 1 millisecond time. It may depend on how clean or whether or not you have the nucleation center, but usually at least you will need like a 1 millisecond for the incubation or the growth time. All right. So, however, in the simulations, in these atomic simulations, I have repeatedly emphasized that we can, because of the small times that you can simulate up to maybe 1 nanosecond. All right. So in terms of time scale, this is much shorter. All right. So therefore, during your simulations, you may not have any kind of the phase transition from the solid to the liquid. So therefore, we need to raise the temperature far further above the melting point, such that nucleation occurs instantly or within the very short time scale. All right. So this is achieved by raising your temperature like above the 1000 Kelvin above the melting temperature. So this is simply unrealistic simulations. However, it requires that you just shuffle up the structure and have the to have the liquid phase at high temperature. All right. So we call this a superheating, right? Superheating. So it's far above the melting point. So once you raise your temperature, unrealistically, then it will melt instantly. All right, and then you equilibrate for the time being. Then you have the liquid phase, right? And then next you lower your temperature to the target temperature, maybe close to the melting point. All right. So in that case, since you are just lowering the temperature from the liquid within the liquid phase, okay, high temperature liquid to low temperature liquid. In that case, this equilibration will it can occur within a very short time scale. All right. So therefore, this is the typical way that you achieve the liquid phase. And the time to reach the equilibrium state requires various tests because it depends on the system or case by case. So you check various things such that, for example, the energy, or maybe if you are serious, then you can calculate the self-diffusion coefficient such that it is still constant. All right. Okay. So all right. So then once you have this liquid structure, then you can analyze its structure. Since in the liquid phase, atoms are just moving around, we do not have such an ordered phase like the crystalline structure. Okay. But however, it is not totally disordered. Okay. So for example, atoms are moving around, but let's suppose that you have just one atom fixed here, right? So, or maybe you can move your camera around to track one of the atoms. Then these atoms are at the center fixed, and within this frame, the atoms are, for example, there's a first shell, or maybe nearest the neighbor atoms with a bond that is at the bond length that is very similar to the crystalline phase, because there's an optimal atomic bonding distance in the crystalline phase. So in the liquid phase, you have a similar the bond lengths. So within the bond lengths, but still the atoms can rotate or slightly move around, or maybe sometimes it can exchange the site with the atoms outside the first shell. All right, so it's dynamically shuffling. However, on average or in a short time scale, you have a the first shell more or less well formed around the center of the atom. All right, so and since this is a liquid phase, the energy of each atom is not a constant. Okay, so it has high temperature, so it can have high speed or low speed, and therefore the bond lengths between the equilibrium bond lengths can also maybe slightly vary or has some of the range that atoms can sometimes closer, sometimes is farther. All right. Okay. So the first shell will be formed, and then you have the second shell. Okay. So around the first shell, there is another atom which is actually the nearest neighbor of the atoms in the first shell. Okay, and they form the second shell. And because of this, this dynamic structure of the first shell, the second shell is more broadened than the first shell. All right, so it has a more wider range of the center of the mass distribution. Okay, all right. So this is the typical picture of the structures in the liquid phase. Even though it is dynamic, we can somehow extract average or some of the characteristic feature of the liquid phase. Okay, so in order to quantify this distribution, we first define this NR. Okay, so NR is the number of atoms within a radius R, within a sphere of the radius R. Okay, so in here, this is the R, and this NR is the number of atoms within this sphere. Okay, then we take a slightly longer radius, N plus RDR, and take the difference from this NR plus DR and NR. Okay, so this number is actually corresponded to number of atoms in this thin shell with the radius of the DR, or thickness of DR. Okay, so these three, the below atoms, are actually belong to this thin shell. Okay, so this is the number, and so it's D and R. And since the surface area is proportional to the 4 pi r square, so you extracted this, and this is thickness. So this 4 pi r square times dr is the volume of this thin shell. All right. So this coefficient, therefore, this is the reference side is the number of atoms in the shell, and this 4 pi r square and the dr, this is the volume. All right. So the gr in this coefficient should correspond to the mean distance or the average distance in the shell. All right, so you understand, right? Number of atoms, this is the volume, and so this should correspond to the density, right? Average density. So this GR is called the radial distribution function. So it basically indicates the density at the R distance from a certain atom, or every atom in the liquid. Okay. All right. So RDF, or since it corresponds to the pair or the distribution function between the two atoms or the atom pair, so this is also called atomic pair correlation function. Okay. In this figure, all right, so at the center of mass, this is R equals 0. This is the center, and the first shell have the sharp distribution, all right, so which is indicated by this shade of the first peak, and this second shell is indicated by this second broad, a little bit shorter but wider distribution. Okay, and this is the third, maybe the third shell. Okay, so combining this first shell, second shell, etc., you have this atomic correlation function in this outline here. All right, so it goes up and deep and up and down. Okay, so this is the first shell, this is the second shell. All right. In the solid phase, since solid has specific density, specific distance distribution, so it has only one sharp delta functions along these radial functions. But in the case of the liquid, you have this broadened distribution function. All right. So during the practice, you will compare this RDF of the solid and the liquid, and they look closer, but it's a little bit distribution, more wider, just broadened distribution in the liquid phase. All right. So from this radial distribution function, you can read what is the center of the first shell, what is the center of the second shell, or whether it is sharp or it is wider, or how many atoms in around the certain atoms, or how many atoms in the first shell by integrating this first peak. All right, so you can extract various useful information from this distribution. Or sometimes this GR is normalized by the average density. This average density because as L goes infinite, then this density correlation function converges to a constant value, all right, which corresponds to the density of the liquid. Okay, so simply, by dividing the total number of atoms with the volume of the liquid. Okay, so by normalizing this GR by with rho 0, then the GR should converge to the 1, and the GR has the meaning of how big or small is at the density at a certain location. All right. So this is the region with the density with higher density than the average density, and this is this region is the density with low the density. All right. Okay. All right. And one important thing is that this GR is actually can be obtained by experiment, right? There's various kind of neutron diffraction or X-ray diffraction which can extract this radial distribution function, all right? By just shining the light onto the liquid phase, you have this diffraction pattern. Since it is disorderly system, you have some of the circle patterns, and then by inverse Fourier transform, you can obtain this radial distribution function. All right. So this is the one you can directly compare with the experiment. Okay. So and the second quantity of the liquid phase is the mean scale displacement. As I mentioned before, these atoms in the liquid phase can move around rather freely, or okay. So suppose that you are tracing one atom here. This is the position at the t equals 0. Then it will move around, but it always constantly hit or collide with other atoms in the liquid phase. Therefore, it changes direction randomly, right? Okay, like in a Brownian motion. And at the time, after time of the t, it will reach in this position. Okay, so difference between these two positions is indicated by this RT, and by taking the square of this distance, and averaging about all the atoms in the liquid, you are obtaining this mean square displacement at the time t. All right. So, and as a function of the time t, you can plot this mean square displacement, and it will look like that. So, it will be after some of the initial or diffusion, then it will show more or less constant or linear slope with this r square with respect to the temperature, the time t. Okay, so this is called the diffusive behavior of the diffusion. And in contrast, in the gas phase, since all this in the gas phase you have very little atoms, so this collision occurs very rarely. All right. So therefore, in most of the time, atoms just ballistic motion is constant without any external perturbation. It will go as constant. The velocity is constant motion. Okay, so in that case, since this is the square, then as a function of the time t, this gas phase will be like the distance will go like a t square. All right. So this behavior, the motion, constant velocity without much perturbation. This is called the ballistic motion, like projectile. Okay. So in the gas phase, it shows the ballistic behavior or the t-square behavior in this for this mean square displacement. In the case of solid, since the solid atoms are just vibrating at a fixed position, all right. So therefore, it will show this kind of the sinusoidal or the oscillative behavior, which is characteristic of the phonovibration. All right, and this amplitude of this vibration is typically the thermal energy of the vibration. All right, in the solid, so therefore it is fixed at a constant value in the case of solid. All right, so the solid, liquid, and gas shows a very different behavior in the mean square displacement. All right, so during the first session, you will calculate the diffusion coefficient and the radial distribution function of the liquid aluminum at 943 Kelvin, which is the above the experimental melting point of the 933 Kelvin. And the temperature protocol you will follow, as I mentioned, you need the superheating in the initial time. So you will melt your system at 1200 Kelvin, right? So which is much higher than this temperature. And then you will equilibrate about around 10 picosecond and cooling it to 943 Kelvin instantly. And then you equilibrate at this target temperature for the 10 picosecond. Okay, so this is a typical way you simulate the liquid phase. You're superheating, and then after equilibration, you go down to the target temperature and you equilibrate. All right, so this is the input file, and this is the movie. So it starts from the solid, and it's superheating. So you can see that even though the temperature is 1300 Kelvin, the atoms are still more or less fixed or bound at their crystalline site. All right, not much perturbation. You need some time, even at this high temperature. You need some simulation time to really truly obtain the liquid phase. Still crystalline, right? Still crystalline. Now you have this liquid phase. All right, atoms are departing from their original site. Okay, all right, it's a site, and now you have the liquid phase, and you have cooled down to 900 Kelvin, and you equilibrate. And you can also see these boxes, simulation boxes are oscillating, right? It's according to the relevant stress component or external pressure. All right, okay, so if you trace the total energy per atom as function of the temperature time t, then this at this preheating or the pre-melting or superheating stage, in the beginning you still have the crystalline structure, and at some time instantly it will go up, indicating that it starts to melt. All right, and then so I think that you have to actually increase the this simulation time a little bit longer actually. I'm not sure why we have stopped here, but I think at least you need to go to at least 10 picosecond more, okay, to fully equilibrate at 1200 Kelvin. All right, then am I right? Okay, and then you gradually over 5 picosecond you gradually cool down to your target temperature. All right, and also you can see that this is the temperature or dose-Huber thermostat. On average is 1200 Kelvin, and it starts to cool down. All right, and then finally you are reaching at 943 Kelvin. All right, and this is the lattice parameter. Okay, and so you have this, since at the high temperature you have the increase of your lattice parameter, and it's cooling down, and now finally you have this liquid simulation. This lattice parameter on average is 4.23 angstrom, and from this lattice, the mean lattice parameter, you can obtain the average liquid density, which is calculated by 2.36 gram per cubic centimeter, which is compares favorably with the experimental value, and also it is meaningfully smaller than the solid density of 2.44 gram per cubic centimeter. All right, so this is the how you obtain this liquid structure, and this is mean square displacement. You may need a VM software to calculate them, and you can calculate this VMD or mean square displacement. You can obtain directly from the lamps. For the diffusion coefficient, you need a VMD software visualizer, and so this is the radial distribution you obtained in VMD. And this is the structure, and you can see that this is the typical liquid structure, and this is the first shell, and this is the second shell. All right, and your GR is normalized by the mean density, so it is has the constant value of the 1 here. And in comparison, in the figure in the bottom, this is the GR of the solid, and since the solid has just the delta function like a distribution, so is in fact it is just one the sharp line, but for the visual purpose we have a slightly broadened. Okay, so in the solid you have first nearest neighbor, second nearest neighbor, third nearest neighbor. You have the specific only the GR at the peak at the specific bounding distance, and you can see that in the liquid phase there are basically the broadened. All right, so the liquid is radial distribution is a broadened version of the solid distribution function. All right, so the peak position here occurs at 2.8 angstrom. So therefore, this should correspond to the average nearest neighbor distance of the liquid. All right, which is maybe slightly longer than the solid phase. And also you can obtain the coordination number. Coordination number is the number of atoms in the first shell. Okay, so in the first shell you have more or less some well-defined number of the atoms, right? Even though it is dynamic, okay, it is not fixed. So atoms are exchanging their sites. However, on average you have the specific number of atoms in the first shell, right? So this first shell, or this is called the coordination number, like in a solid. And in the liquid phase, although there is not a specific, mathematically the precise definition, but usually in most cases we take this first dip, okay, it's the first minimum, and we integrate this GR with respect to R from the 0 to this up to this first dip position, and then it will give you the number of the atoms within the first shell. So this is the typical, the conventional way to extract coordination number from this RDF. All right. Okay. So then also within the VMD, you have this integrated. Okay. So this is the integrated GR. If you integrate this GR and this, then it will give you the NR, the number of the atoms. So this is the position of the first dip. So the number corresponding to here is about 12. Okay, so this 12 is the average coordination number in the liquid phase. You can compare this with the solid phase. In the solid, of course, it's aluminum efficient structure, and therefore in the first shell you have the 12 nearest neighbor atoms, right? Again, it is exactly is given by this figure here. All right, so you have the similar number of atoms in the liquid phase. So this is typical. In the liquid phase, even though it is dynamic system and also disordered system, its first shell is pretty much similar to the solid phase. All right, similar number of the coordination number, and also similar the bonding distance. All right, so this is the in most cases this is true, but sometimes you have a quite different order. All right, like a silicon. All right, so and also from this you can try the crystallization of the aluminum. So you have the liquid phase, and if you cool it down, then below the melting point you should observe the crystallization of the aluminum. All right, but here the key question is the fast or the speed of the cooling down. All right, so in reality, when you in your typical in experiment, when you cool it down, then it takes quite a long time, like over 100 degrees Kelvin, 100 Kelvin. Maybe you need like 1 hour to cool down 100 Kelvin. But in some of the very specific, all right. But in some specific experiment, you can achieve extremely high cooling rate. This is used in obtaining the amorphous structure from the liquid phase. But even in that case, the cooling rate you can achieve is about 1 Kelvin per nanosecond. Of course, this is extremely fast cooling rate. Like this means that for 1 second you are cooling down to 1 billion, right? 1 billion Kelvin, right? So this is extremely fast cooling rate. However, still in terms of the computational simulation, this is quite a slow cooling speed, because our simulation, well, 1 nanosecond, it will take like maybe several hours. Okay, so cooling down to like 100 Kelvin, maybe at this the realistic cooling rate or fastest cooling rate in experiment, you will need at least several months of time to really cool down. Okay, so we cannot avoid increasing the cooling rate, maybe unrealistically, maybe 1,000 times. And for instance, here the cooling rate that we are using is 0.4 Kelvin per picosecond, so it is about 400 times faster than fastest cooling rate in experiment. Okay, all right, but this we cannot overcome this time scale, the problem. So the only thing that we can expect is that, well, I mean that's the thing that we are interested in shows the similar behavior between this our cooling rate and the realistic cooling rate. Okay, so there's this issue of the cooling rate, and still you can observe the essential features. So one consequence of such a extremely high cooling rate is that, so suppose that this is the melting point. So this is the melting point. So you are starting from the liquid above the melting point. You will cool it down. So maybe in principle you should observe the crystallization at this temperature, or maybe the temperature that is slightly below the melting point. All right. So this happens in real system. However, in our case, since we are cooling it so fast that the crystallization does not occur exactly at the melting point, but far below the melting point. So you have super cooled liquid. Okay, so maybe that below, maybe the 50 Kelvin or 100 Kelvin below the melting point, you are starting to observe the crystallization. All right, so this is because of the unrealistically fast cooling rate. All right, so okay, but in any way you can observe the crystallization. All right, so this is the liquid, so you are the learning this movie in a very fast time, and maybe it goes crossing the melting point, and now you can see a little bit warm. Okay, so instantly you are observing this crystallization, right? You can see that. Okay, still the liquid, then instantly it crystallizes. All right. Okay. However, actually, but this is the there is an artifact of this supercell. I mean, in your simulations, we are imposing the periodic boundary condition. So, this is too small, right? So the nucleation and or crystallization, occurs instantly, but this is an artifact of the periodic boundary condition. What happens in real system is that you have the small nucleus at a certain point, and this nucleus will grow, right? So you can also see this from these very large cell simulations. So in the beginning, this is the liquid phase, and at some time, right? Okay, so here you can now see, or if we go back, so this is a crystalline state, right? Crystalline state. You can see the ordered structures, right? Or it happens that it has the one nucleus at this corner of the simulation box, okay, which is repeated at these different corners. All right, and then this small nucleus grow, right? It grows, and eventually it will take up the whole, your system, right? So even in this quite a big supercell, for the simulation sense, we have just only one nucleus site, and it will grow. It's gone. All right. Okay. So this is the frames or the snapshots. This is the zero starting. The T equals 0 and the 560 Kelvin. So temperature protocol was that you are starting from the 943 Kelvin and you cool it down to 300 Kelvin. It is cooling rate. And only at the temperature of the 560 Kelvin, which is the, maybe more than 300 Kelvin below the melting point. So this is extremely super cooled liquid. And then you have this nucleus site, and it grow, and it's fully crystallized. All right. So you can observe a basic, the nucleation and growth process in this simulation. Okay. So. Here we change the topic to the water system. All right. So the water is the most well-known liquid structure, and also it is very important in many applications, and also in the atomic simulation. So people are trying to develop the accurate but efficient potential or for atomic force field for the water system, and there are many versions about that. And the main difference is that how to put the partial charges, or how you represent the charge distribution of the water molecules. Like if you are simulating your because hydrogen bonding is basically electrostatic interaction. Right? Hydrogen is plus charge. Oxygen is minus charge. So this is attraction between the plus and minus charge. It is the core part of the hydrogen bonding. And so it is critical how to describe the continuous charge distribution in terms of the point charges that we can use in the classical simulation. And the 3 site means that you have this HOH 3 site, and this 4 site means that you have the another charge center that is just below the oxygen. And this 5 site means that you have these 2 charges which may represent the lone pairs, so-called lone pairs of the oxygen atoms, or which is actually characteristic of the chalcogen atoms. And also 6 site, which is very detailed description of the charge distribution around the oxygen atoms. All right. So with this charge distribution, you can also add like the van der Waals interaction, and also the bonding between the oxygen and the hydrogen, also the angle term between HOH. Okay, so to represent this characteristic angle of the water molecule. All right. So this is the typical TIP. Okay, so 3P, or this 3P means a 3-point charge model. Okay, and these are the various parameters. And maybe actually this is the first page is already implemented in the LAMS program, right? Okay. And this is reference. Okay, so and this is the simulation of the water molecule. All right, so yeah, okay, so this is water molecule. Okay, and you can see that water molecules are moving around. One thing that actually you can notice is that the rotation of the water molecule actually occurs very rarely, right? In most, it's like some rigid motion in most cases, but it rotates very, very few times. Okay, can you see from this? Yeah. This is because in order to rotate, you have to break hydrogen bonding and reform another hydrogen bonding. So it costs energy, right? So it actually happens quite rarely, the rotation of the water molecule. All right? Okay. All right. And also, this is just an equilibrium state of the water. But for the freezing of this, okay, why not we share this? So one of the very old problem is to simulate the freezing of the water molecule, right? And also we have the density anomaly in the freezing of the water molecule. So if it freezes, then actually the density decreases, right? Density decreases, or volume expand. Volume expand, right? So to simulate this is a very old problem, but because of this typical the length or the time scale difference, not many people have succeeded in it. But very recently, some Japanese group have successfully simulated the freezing of the water molecule, and they published this paper in Nature. Just simulation, right? Here you can see that this hydrogen bonding is formed here, and it grows, right, over the whole liquid phase. All right. So from this simulation, they could observe the detailed mechanism of the freezing of the water. All right. So this is very important simulation. All right. So. All right. So during the first session, you will learn about this water model and obtain the density. Okay. So the last topic today. Okay, so this is amorphous material. So the definition of the amorphous material is that it is basically solid, but it does not have the long-range odor that is characteristic of a crystal. For instance, this is a silicon atoms, so it has an odor that is far extend beyond its nearest neighbor, right? So it has the well-developed odor throughout the whole space. This is a characteristic of the crystal, right? The long-range odor. But however, in the case of the amorphous materials, you have the maybe short-range odor, which is the tetrahedral bonding in the case of the silicon, but just going beyond first neighbor or maybe the medium, the second nearest neighbor, you have totally no odor. Okay, so every atom has a different, the distribution of the atoms if it goes outside the first shell or the second shell. All right, so this is the amorphous material, and depending on the type of the structure, we are actually differentiated three types of the amorphous model. The first one is continuous random natural model. This is the applicable to the covalently bonded glasses like the silicon. So in this case, you have the tetrahedral bonding, which is well made for every atom, but the angle of the tetrahedral bonding between the first and the second, the neighbor, it can actually rotate. All right, so it continuously rotates. Right, so this is continuous random natural model, and the random coil model is best represented by this picture here. Which is represent this polymeric glasses, right? So just random coil, like your everyday. You can see this kind of entanglement in everyday life. Okay, or random close packing, which is a characteristic to the metallic system. Most difficult, the metallic glasses. In this case, you have the close packing model, but it is not really FCC or HCP-like. It is compact structure, but it is disordered if it goes beyond the first shell. So if you mix up various kind of the metal atoms, you can have this the metallic glasses. Okay, so the most well-known system would be the gold and silicon metallic glass, or the okay. All right. So these days we have seen numerous applications of the amorphous material. So this is the something that you can achieve the properties that is not actually not seen in the crystalline phase. For instance, the amorphous silicon oxide, this is the glass. So you may have seen this kind of the manufacturing process of the glass. You start from the melting or the liquid phase of the silicon dioxide, and then you cool it down and you make a forms, right? Since it is amorphous structure, you can change the shape, in any way that you want. Okay, so this is the typical of the amorphous structure. And also in the solar cell, we widely use this hydrogenated amorphous silicon. Okay, and also in the display, we use in some of the OLED TV, and also some of the very high-end desktop. We now have these materials of the amorphous indium gallium zinc oxide that replace amorphous silicon. All right, actually it is already used in the industry. And also, of course, Galaxy or better recent iPhone 10, it uses this OLED display, right, which is made of amorphous organic films. Like you see here, this is the layer amorphous organic molecules that is stacked in a random way, and you have this electron hole transport across this amorphous layer. All right. This material, this GS2 germanium antimony telluride, GS225, this material is now used in the phase change material, which actually exploit these physical properties of the crystalline and amorphous phases that are quite different. So in the crystalline phase, like in rock salt structure, this chalcogenide material, and it has high reflectivity, optical property, and it has a low resistance electrically, right? On the other hand, in amorphous structure, it has low reflectivity optically and high resistance electrically. So it has a contrasting the properties between the crystalline and amorphous phase. And the one important feature of this chalcogenide material is that you can easily change its phases, the melt, quench, and the annealing, right? So by applying high electric pulse or laser pulse, you can instantly melt this crystal structure, and you cool it down, then it becomes amorphous structure. And more surprisingly, if you anneal your system at a slightly lower temperature or slightly above the glass transition temperature, then it changes into crystalline phase that is the more stable in energy. Okay. So, but this crystallization happens in a very short time, like maybe some tens of nanoseconds, which is very fast. So it can use in even this electrical application like the memory, non-volatile memory. Okay, so it is one of the key materials in the next generation, the memory material. All right, so there are numerous applications in structure. So, but the problem of this the amorphous structure is that it does not have the specific or well-defined crystal the atomic positions. So remember that when we simulate, what we need in this atomic simulation, what we need is that in the beginning we need is the position of the atoms, right? So in the crystalline structure, we already know if we have FCC, BCC, or a kind of structure, you already have this atomic positions. You just optimize the lattice parameter or a slight variation of the atomic positions. But in the case of amorphous structure, there's no such information, right? One thing that you know is that it is amorphous, right? So therefore, in the simulations, we obtain this structure just from the multi-quench simulations, just following the experimental procedure of this generation of amorphous material. You start from the melting point, and then you cool it down, and below the glass transition temperature, you are obtaining this amorphous structure, right? But here again, the problem is about this cooling rate. The cooling rate is unrealistically high compared to the experiment. So you just pray that it will be okay, right? You have to check it in various ways. All right, and so also in the amorphous structures, similar to the liquid structure, you have the broadened distribution function, right? It is not dynamically changing, but it should be because every atom has a different neighboring configuration. So on average, it has a radial distribution function that is similar to the liquid phase. All right. So your task is to obtain this RDF for the unprocessed silicon, and you melt, cool it, the melt and the quench, and so you obtain this unprocessed structure. And this is the distance distribution RDF for the crystalline structure, and this is the RDF for the unprocessed structure. You can see that this is very similar to the liquid phase. All right. Okay. And in the unprocessed structure, you can see that every atom is actually has or mostly tetrahedral or fourfold coordination. But some of the some of the defective site, you have the threefold coordinated or fivefold coordinated. So this is a structural defect in terms of amorphous silicon, right? So this is the typical of this amorphous structure. So this is, since it is not a crystalline structure, it has some of the variation in the structure, and sometimes you have this kind of the coordination defect. And in fact, this is the main problem of using the amorphous silicon in the industrial applications or electrical applications, because this kind of the defect site can be charged plus or minus, which impeding or which hinders the motion of the electrons that is moving along this material because it's charge defect. So that's why people are hydrogenating your amorphous silicon, right? So in this case, using just by providing hydrogen, then this hydrogen will effectively passivate some of this kind of the structural defect site, and so it removes those charge defect. All right. So then, only after that you can obtain the significant electron mobility. And also you can obtain this angle distribution function, and you can see that it is peaked at 109.5 degree, which is exact the angle of the tetrahedral bonding. Okay, so the basic unit of this amorphous structure is the tetrahedral, although it is sometimes a little bit distorted. All right, so this is the the evidence of continuous random natural model. All right, okay, so that was the end of the simulation of the liquid. Any question?
So today we are gonna do 3 practice. One is aluminum liquid and water liquid, and then we're gonna do silicon amorphous simulations. So the first one is, as you already seen from the previous lecture, is aluminum liquid. So this is a input file. So as usual, we're gonna use EAM potential for aluminum metal, and we're gonna make a 3x3 supercell with replicate command, because we're gonna need a larger cell to simulate liquid or amorphous. And then we're gonna set the lattice parameters, and then we will need this movie file later on to analyze the RDF. So we're gonna make it dump the movie file with dump movie command. And here we print out some of the variables with my fixed print command. So here we're gonna print 4 variables, which is steps and temperature and total energy divided by the number of atoms, and this Lx parameter. Lx is the size of the box in the x direction, and since we made this 3x3 supercell, we have to divide it by 3 to obtain the lattice parameter. So we're gonna make it dump the lattice parameter with this Lx/3 command. And 10 here means that we're gonna make it dump these variables with every 10 steps. So this is for the movie command, and this myprint command is to obtain the data from the simulation. And then we're gonna start to set up this simulation to run the liquid aluminum simulations. So first we have to create the velocities up to, here we set this temperature to 2400 Kelvin. So as we already mentioned last lecture, we can make a very high temperature to start with, and it's okay because it's gonna equilibrate very quickly. And then we're gonna do this Mpt simulation with superheated temperature of 1200 Kelvin. So here it is the Mpt command. The former part of the command is same with the Mpt command. Here we set up the temperature first, and the first one is the starting temperature, which is 1200 Kelvin, and the second number is the end temperature, which is the same temperature, the starting temperature, and this number is the damping constant of temperature. And since we are doing the time step of the simulation is 1 femtosecond, the damping term of the temperature is going to be 100 femtoseconds. And then the latter part is for the pressure part of the Mpt command. So here we're going to apply the isotropic pressure over the simulation cell. So the iso means that we're going to apply the isotropic or hydrostatic pressure, and the next number is the starting pressure. So it is 0, so we're gonna add no external pressure on the simulation. We're just gonna let it vibrate by itself. And the next number is the final pressure, which is also 0. And the last number is the damping term for the pressure. And usually we set the damping term for the pressure is 1000 times the time step, so it's gonna be 1 picosecond. So with this Mpt ensemble, we're gonna run the simulation for 10 picoseconds, and then we change it to change the temperature to 943 Kelvin, which is 10 Kelvin more than the melting point, which is still liquid, but we're gonna make it more realistic temperature to this 900 Kelvin. And the rest is same. The only exception is this temperature term. And we're gonna run it for 5 picosecond. And since we have arrived to the target temperature here, and the atoms are now in liquid phase, we are gonna calculate the mean square distance, and we can do it with the LAMPS implemented code. This is the compute command. If you look it up on the internet, the manual, there are some of the variables or some of the terms that you can compute and make it print out for you. And mean square distance is one of it. About this later part, I'm gonna explain in the next slide. So you already saw this movie. So, as I said, the compute command make it compute some variables and then print it out for you. So here we used MSD command. So here we make a print for C my MSD 4, and as implemented, the compute MSD gives you 4 values for you, which is the mean square distance for x direction and y direction and z direction, and the last one is the total mean square displacement. Here we want this total mean square displacement, so we're gonna make it print out the 4th value of the MSD. So if you do this, like fix my print and let it print out the 4th value of the my MSD and this 100 here, then we will gonna print out this mean square distance every 10 steps to the file name of e.dat. But instead of we just printing out the MSD, we're gonna average the value for certain time interval and then print out this averaged value instead of the MSD of certain point. So in order to do that, we have to use this fix average per time command. So it's gonna print out some value of variables with averaged for some time period with some time interval. So here you have to give 3 numbers here. So the third one is the n frequency. So the third one is how frequently you want it to print out the certain variable. So if you write 100 here, then it will gonna give you the value every 100 steps. And the second number is how many steps, how many variables you want it to average for you. So here you give 6, so it will gonna give you the average value of 6 MSDs. And the first number is the time interval you want it to give. So if you give it 2 here, it will gonna compute the MSD every 2 intervals. So with 2, 6, and 100, for example, it will gonna average the value of every it will gonna average the value of 90 to 100 with 6 values and calculate the average and print it out for you. So in the input file here, actually there is a typo in your input file. It should be 1000 and 1000, but if you look it up on the practice material on the homepage, it is 1001 and 1000. But the result is similar, but anyways, it is not what we meant it, so you may want to change it to this 1 and 1000, 1000. So it will gonna give you the MSD of average values. And finally, we have to do the Mpt simulation within the target temperature and target pressure for 10 picoseconds. So So the simulation is done, and there's gonna be 4 output files, and one is the log file, and there's e.dat, which contains steps and temperature and energy and the lattice constant. And if you bring it to the Excel file and then draw the relation like this, it will gonna give you the temperature and total energy and the lattice constant like this. Same here. So you can calculate the lattice constant of the aluminum liquid. And there's going to be MSD file, which is like this. The file is going to be like this, but if you want to set the 15 picosecond time as the 0 time, then you just have to subtract it to be 0 and then plot it, and then it's gonna be like this. And then you can calculate the self-diffusion coefficient from this MSD data, the slope. Next, we are gonna do the RDF with VMD. So there's gonna be a movie file here. If you bring it to VMD, it's the same movie file from the PPT. But what we are going to do here is to draw the RDF graph with VMD. So click the, 다 하셨나요? 다 여셨나요? 해도 되죠? 네. Click the extension here and analysis, and click the RDF here with your pair distribution function GR. And there's going to be another thing here. And click here to select the molecule you want to analyze. And it's going to be the movie we just created. And here we have to choose which atom you want to draw RDF with. Here we only have aluminum here, so we'll just do all. And we can choose the time interval where we want to average to get the RDF. So here we want to draw the RDF of liquid aluminum, so we have to choose the later part of the simulation, which is the aluminum of 900 kelvins. So it's gonna be in these frames. It's gonna be from frame 150 to the last one. -1 means last step. So if you click compute GR, then it will show you this RDF graph. Just like you have already learned, there's going to be a peak here and there's going to be a dip here. And the bond length is shown here, about 3.7 or 8 angstrom. And next, If you want to know the coordination number, then you have to integrate the RDF graph. So the VMD program also give you the integrated RDFs. If you want to do that, you have to check here, display integrated RG. Check here. Here. And then compute. Then it will not only give you the RDF, but also gives you this integrated value. So we already know that the bond length is about 3.8 something. So if you look it up here and check the integrated value, then it's gonna be 12, which is the coordination number of aluminum. So that's how you get the bond length and the coordination number with RDF. Here's the input file for the crystallization of aluminum. If you want to try this, you can, but we're not gonna do this here because it's gonna take too long. You can see that we have to do this for more than 1 nanosecond. So it's gonna take some while, so we're not gonna do this here, but if you want to try this, you can do it home. Next one is simulation of water liquid. So this is the input file. This simulation is gonna take some while, so I will just make it run, then explain the input file. You might want to run it now too, because it's going to take some while. So you can see that it is quite slow. This is slow because the potential is more complicated than the aluminum potential or silicon or something like that. So here we use the units of wear, not metal. This unit is frequently used for the simulation of molecules. So the units of or the physical constants are different, so you have to be careful. For example, for metal, the energy was EV, but now it is Kelvin per mole. And in metal, the time was picoseconds, and now it's femtoseconds. So it is a little bit confusing, but you have to be careful. So one of the common mistakes you might make is confusing of the units. For example, here with Mpt comment, the damping term is same with the previous one. It is 100 femtoseconds, but now it is in the units of year, so it's going to be 100 instead of 0.1. So you may confuse this, but you have to be careful. And the next command is going to be atom style full. We didn't use the atom style in the previous input files, so it was atomic. The default atom style is atomic. The atomic so if you look it up for the aluminum atoms, here you give the ID of atom and the type of atom, and then just the position of the atoms. So it's going to be just 5 numbers. But with atom style full, it's gonna be a lot of informations, which is the charge and the bond and the angle and which molecule that the atom is included, and all of this information should be included in the input file, data file. So the first one is going to be the ID of the atom, and the second one is going to be which molecule the atom is included. So these three atoms are included in the first molecule, and then these three atoms are included in the second molecule, or something like that. So you designated the molecules for these simulations, unlike the previous ones, because this is more. And the third one is going to be the type of the atoms, so whether it's going to be oxygen or hydrogen or something like that. And the next one is going to be the charge of the atoms and then the positions. So it's a lot more informations, and all of the informations are included in the data file. And then here, instead of bringing up the potential file in the info file, we're gonna build up the potential within the info file here. So you have to set the bond style and angle style and pair style are here in the info file. So here, for the bond style, we're going to use the harmonic bond, which is like this. So the R0 is the equilibrium position of the bond length. And same with the angle style, is also the harmonic angle. And the pair style, which is the potential for the intermolecular potential. The bond style and the angle style was the intramolecular potential, and the pair style is going to be the intermolecular potential. It's going to be LJ, charm, Coulomb, long potential style. And all these are the parameters for the potential. So here, basically, we're going to use this type of potential, which is tip 3P, and all the parameters are set up here in this command. So the bond coefficient, which is the K, R, and the R0 and something like that, are set up here, and the angle coefficient for this term is here, and the pair coefficient, which is the sigma and epsilon 0 for the sigma and epsilon for the LJ potential is set up here for HH, OO, and OH terms. And here with K-space style, we're gonna calculate this Coulomb potential term. So here, the potential is set up within the info file, and the rest is similar. You dump the movie file and you minimize the structure before you run these simulations with temperature, because it may be unstable at the first time. And then you are gonna use the myprint fixed print command to make it print out the density for you. And then it's gonna be Mpt Simulation. And like I said, you have to be careful for the units, and rest is similar. The simulation is still not done. We have to wait too long, so I'm just gonna end the simulation here and just use the files that I brought. So this is gonna be the e.dat file. You make it print out the steps, temperature, total energy per atom, and density. So you can draw the relation of steps and density here, and you get the equilibrated density of the water. Like here. You can get the density. So the last one is for the amorphous silicon. This simulation is also quite slow, so I'm gonna run it first and then explain the input file. This simulation is slow because we have to run for quite long time period to make it the melt and quench simulations, especially the quenching simulations. Here we are using the metal unit, and there's a data file for silicon, and we're going to use the torus of potential, and we're going to make the 555 supercell because we need a large supercell to simulate the liquids and amorphous, as you already learned. And here we're just setting the lattice constant, and then like the aluminum liquids, we will need the movie file to analyze the RDF. So we will make it dump the movie file here, and the rest is same with aluminum liquid. Here we run the simulation for 3 parts. First part is for the melting of silicon, which is done in 4,500 Kelvin, which is really high temperature. As I remember, the melting temperature of silicon is about 2,000 Kelvin, right? 2,000 or 3,000. But we have to super heat it to make it liquid. And the simulation is done for 10 picoseconds, and then it's going to be the quenching of the silicon here. So it's going to be much longer than the liquid simulations, which is going to be 70 picoseconds, and the temperature is from 4,000 Kelvin to 300 Kelvins, with the quenching rate of 60 Kelvin per picosecond, which is really fast. And then we have to equilibrate these structure in 300 Kelvin for 10 picosecond, and you get the amorphous structures, which is going to be like this. And the simulation is still going. So I'm just gonna use the file that I just brought. So after the simulation, it will give you the movie file of actually I think I forgot to brought this movie file for silicon amorphous, so we have to wait.